In the last few classes, especially the last week, completely 3 classes, we were looked into engineering mechanics and recap of those parts of engineering mechanics which is going to help us in understanding strength of material better, right? And we had few examples I've given. I have given more than what you have read in your undergrad in your engineering mechanics course. So there was a little bit of new things, new ideas, as well as a lot of old ideas that that form the lectures in the last 3 to 4 classes, right? I think this should be 5, right? Because we had 4 classes in the last week, so this should be 5. One of the class did not happen because of the internet issues at my end. Nevertheless, we are probably one day, late in our lectures. Today, we are going to start with understanding of what is strength of material and what this whole course is going to give you. All right. What as a faculty I will expect at the end of this course that a student or whoever taking this course would know at the end of the semester, and what you are expected to learn. So the objectives from your side will be clear. The objectives from my side, that this is what I want to teach to my students, that at the end of the semester they should be thorough with these understandings and these concepts. Okay, and from your side also, if you learn more than that, it's always good, but make sure that you don't learn less than that, right? If you learn more than that, it's good for you, it's good for me. But if you learn less than that, then when you go through your ME courses next semester onward, you will find difficulty in grasping few concepts, and then those teachers will not be very happy with our teaching. Okay, so both way it's going to harm. It's going to harm applied mechanics prestige, that they did not do a good job, and it's going to harm you because you are the student who is going to face the difficulty. So let's make sure that we are thorough with few concepts which we want. One of this concept is stress. Okay, today I will introduce the concept of stress to you, and we will develop on it more in the next class. And by the end of second class, I think you will be thorough with what stress is. But the course as a whole till the end will have stresses as the main concept, along with strength and deformation as a part of the course. Okay, so these 3 important things you probably will understand in this course. One is stress, strain, and deformation, and how are they related, right? So this is overall. So right, so this is what we have in stress part. Okay, not outside stress. In the stress part, this is what we have. And let me not stress you out right now, but this is what we are going to discuss. Just an introduction, which will be today, a little bit of definition of stress, normal stress, and shear stress. Maybe if I can, I'll follow on today. In the next class, we will go into 1D, 2D stresses, then 3D stresses. Okay, and while we discuss these stresses and their relationship with the forces, we have to do a few problems, to make sure that our understanding is clear. And these will be what we follow in the next 2 classes. More relationship on stresses, how you use it for different kind of structures, what else apart from calculating stress that you can use stresses for, will be the part of the full course. Okay, so don't assume that you learn complete stresses in 2 days. It's a progressive thing. You learn in this semester something. You'll learn a little bit more in next time when you do something else, like maybe solid mechanics course or advanced solid mechanics course, or maybe finite element, right? So everywhere you learn a little bit more and you add onto your bag of concept that you have about stresses. Mechanics of materials is one of the name that we use for this course, and or the strength of materials. Both suggest you're talking about materials, right? Either you tell it is a strength of material or you tell it mechanics of material. You have materials common there, so you are talking about materials. Now when I say I'm talking about materials, as a mechanical engineer, we would expect you understand the mechanical behaviors of materials, not the chemical behavior. Okay, So more so on the mechanical behavior of material. So a material can have various kind of behaviors, right? You already have learned in your chemistry, in your physics, that the same material can show various kind of things. So we are not dealing with things that are related to chemistry, okay, like its atomic structure, what it will get solved with, dissolve in, or at what temperature it will get fire. Yeah, fire is part of mechanics of material, but that's not part of this course. Might be later part you can take it. What we are dealing with, the strength of the material. That means how much load it can bear. Okay, how much load I can put onto the material. Right. Our objective is to design some part of a structure or some part of a machine or whatever. Right. Or maybe an aeroplane structure, maybe a naval structure, or it can be a building structure. It can be a machine part. Right. Whatever it is, we need to understand how much load we can give. Okay, same thing if you have you can talk about body biomechanics of bones or other things. So you know that you can take up certain kind of load on your hands, right? Both the hands, and after that your hands started paining a lot. And you also know that if there is a sudden fall of some materials on your hand with certain loads, the hand may break, the bone may break, right? So this characteristics of bone, how much load it can carry before it fails, how much deformation it can go before it fails, are part of our study of mechanics of material. Okay, these are the mechanical characteristics of the material. Okay, so when we say about mechanics of materials, the concepts that we have in mechanics, so we in short we call it mechanics, right? So in mechanics, when you talk about mechanics, we have I divide it, it's my personal choice, into various parts. First part is rigid body mechanics, and the second part is called deformable body mechanics. Okay, what is rigid body mechanics? You all have done it in your engineering mechanics. A rigid body mechanics is when two points in a body doesn't have any relative, 2 points in a body do not have any relative motion about each other, right? They can rotate, but there is no relative motion about between 2 points. It's called rigid body mechanics, right? But in deformable body mechanics, the distance between these 2 points in the body will not be same. It will change. Okay, there is no constant that it has to be same, and therefore it's called deformable body mechanics. So if you have a body and you have 2 points A and B, the distance between these 2 points fixed, right? A to B distance is fixed in rigid body mechanics. But in case of a deformable body mechanics, those 2 points, whatever we were talking about, A and B, the distance AB is not fixed. Okay, it may end out to be same at the end of your analysis, but there may not be any extension, but extension is allowed. Okay, the relative deformation between A and B, A might deform by, let's say, 1 centimeter, B can deform by 2 centimeters. It's not necessary they have to deform in the same direction and they have to deform by same amount. None of these are fixed. So there is between points. This is what is called deformable body mechanics. And as in rigid body mechanics, you have learned that it is divided into two parts. One is statics, the other one is dynamics. When we talk about statics, we talk about only F, summation of F and summation of M should be equal to 0. Now, both of them have two parts. One is called static, the other one is dynamics. And you know the difference, right? In static, we don't have inertia forces coming into action there. And in dynamics, we have inertia forces coming into action. Okay. So that's the main difference between static and dynamics. In static, we look at the equilibrium points of the dynamical system. Okay. So when you say we are at static, we say that the system is not changing with time. Okay. Many of the dynamical problem where inertia forces are much lower, you can represent them as a pseudodynamic or a pseudostatic problem. Okay, because we are assuming that the inertia force contribution of inertia forces are much lower. But in dynamics, they play a huge role, and therefore, dynamics is something that changes with time, right? The properties of the system may change with time, the responses of the system may change with time, the load may change with time, more importantly, okay? The load may change with time, right? So in dynamics, your system, if I assume the system to be, let's say, X, if I assume the system to be X, it is a function of time. In this case, it's not a function of time. Okay. Similarly, for deformable body dynamics, you have statics and dynamics again. Now, you see here, the rigid body dynamics, you did not have to take care of systems that are deforming, right? Flexibility of the system is not there. The system is considered to be rigid. Its stiffness is very, very high. In a deformable body dynamic, the stiffness is moderate so that the body can deform relatively among each other. Where statics deals with SOM is the first course that you do. Solid mechanics or advanced solid mechanics you do in the next part, and then the mechanics of materials. Okay, so it can be divided into two parts: discrete body mechanics and continuous body mechanics. Okay, discrete body mechanics, you might have heard about this name, discrete element methods, and then you have heard about finite element methods. Okay, they take care of the discrete element methods. Discrete body mechanics. That means most of the bodies, or all bodies in solid mechanics, are continuous. Okay, we assume them to be discrete for this, for the ease in solution or to get quick solutions, and we use some methods, some tools to do it. Some of these tools are discrete element method or finite element method. Okay, but we can also solve, very simple problems which are, in continuous domain, and using stress functions. You will learn about stress functions when you do solid mechanics course. There are area stress function, there are shear stress functions. So there are a lot of stress functions that you can use to solve problems related to continuous system. But again, I'll tell you, they are restricted to very simple geometric structures, not very complicated structures. For complicated structures, you definitely get to a formulation and then you have to solve it numerically. Okay, either you start with FEM or you solve using other methods, but finally you have to get back to numerical solution, numerics, to solve your problem, because continuous systems give rise to partial differential equations and they are not easy to solve. Similarly, in dynamics of deformable body mechanics, we have again same thing, continuous mechanics, we call it continuum mechanics. Right, so we have again kinetics and kinematics. That's how we have learned in the dynamics. But when you talk about kinetics and kinematics here, you talk mostly about every point in the structure, right? Here, when we talked about kinetics and kinematics, we talked about the CG of the structure, right? Center of gravity or center of mass of the body. And we assume that every other point on the body behaves similarly as the center of the mass of the body. But in case of deformable bodies, that may not be true. Okay, and if that is not true, then you have to look for every point you're solving. So this will be kinetic of deformable bodies and kinematics of deformable bodies, which you can use again as discrete system or continuous system. Okay, discrete system you have learned, partly there are single degree, you can model them as a single degree of freedom, you can model them as a multi-degree of freedom, but there is a separate solutions available for continuous systems also. Okay, but again, I'll tell you, this will be much tougher than this continuous system, because here there will be another variable that primary variable that will come into picture, that is called time. Right, this is PDE. Right, this will be also PDE for the same structure, but another factor that will come in is time, which will make it a little bit more complicated to solve. So in the beginning of this course, I'm telling you this because whatever we will solve in this course, this is the first course you are taking on deformable body mechanics. You will be solving very simple problems, very easy structures. For complicated structures, you have to look for finite element methods or advanced courses of mechanics. Okay, now strength of material involves two terms. One is called strength and the other is material. Right? For example, I'll give you an example. Let's say you have a chalk with you. Okay, how difficult it is to break a chalk? It's very easy, right? It's very easy. You don't need a lot of force to break it. Now let's say you have the same thickness and same size of a steel rod. Can you break it? You cannot break it. Probably none of you can break it with bare hands, right? So I have just changed the material. Everything else I have kept the same. So with material, the load carrying capacity of the system has changed. There are a lot of behaviors also changed. We'll talk about these behaviors more only after another month, but behavior is also changed. Apart from that, the load carrying capacity also has changed. Therefore, material is important. Let us now take of the same size and thickness of a wood. Okay, will it be easy for you to break? Yes, for some of you it will be easy, you can break it, and some of you may find it a little bit difficult to break it, but finally all of you can probably break it. But it is not as easy as the chalk to be broken, right? So I have given you an example of a chalk or wood and of the same dimension, maybe a steel rod, or aluminum rod. And you found there is a difference between them in terms of load carrying capacity, right, before failure. One of them very easy to fail with your hands. The other one little bit difficult to fail, the wood little bit difficult, but probably you can fail them. But when you come to steel, it's not easy, right? These are three things. Now look at rubber. Let's take another example, rubber. Now when you have rubber, it will be very, soft rubber, not a hard rubber. If you have a soft rubber, it will not be easy to break it, right? It will deform as much as you give force, it will keep on deforming. Right? So this is another aspect of the material. First three material, you said that probably it will break. The first two will definitely break unless the wood is soaked in water. Steel is difficult to break, but you can bend it and probably with some twist here and there you can break it. But the rubber will probably be with hands of that small size will need lot of twist and turn to break, right? It has to tear, and then on the tearing you have to start working to break it, right? So you can see I have told these three examples, these four examples gives you a hint that material is important, right? And in mechanical properties that we are looking at, probably the load carrying capacity, that's the only thing that we understand right now, is different if I change the material, given its shape and size the same. Okay, next class I'll show you one video where we have tested different materials and they broke at different different values of load. I'll show you those videos in the next class. Therefore, strength of the material, strength of a structure depends on what material you choose. And as an engineer, you have to make a choice, right? The client will not give you the choice. Client will leave everything onto you. The client will tell, I need this much loading to be carried by my structure. That's all. For example, a guy who wants to make a hospital, he will come and tell you that I want to make a hospital with 1,000 beds. Okay, there will be 1,000 beds. There will be something around 100 to 200, nurses, or maybe 500 nurses working all the time. At any point of time, 500 nurses may be working, 100 to 400 doctors are working at any time. There will be ward boys and all, and the other things, structures, equipments, everything they will give you. That this is what I want in my hospital to be there at any point of time. Now it is up to you to choose the material, right? And your objective will be to reduce the cost, because client at the end would want that the hospital runs for 100 years without any crack at a lesser cost. And it is your job to make sure to calculate the loads that will come because of 100 beds with 100 patients, and there are so many doctors, so many nurses, so many ward boys, so many equipments. You have to calculate the load that comes onto the structure, apart from wind loads, structural weight, its own weight, maybe seismic load, in the sense if there is an earthquake prone zone, seismic weight, and all those things, blah blah, everything you have to add and come up to a load per floor, per room, per thing you have to design. And then you have to choose your material such that economically you can design the structure and it will survive for a long time. Okay, that's your choice. And you have to also keep in mind the environmental factor. Right? You cannot have a open metallic or open steel in a place where there are a lot of, like Chennai or sea coast, where there is a lot of humidity in the air, right, with a lot of salt, because that will corrode your steel material, iron rods, right? So you cannot keep them open. So you have to understand what you are going to do. So that's a job of an engineer. Same goes for a flight. You take an aeroplane, right? The client will come and tell you, Boeing probably is going to design some aeroplane or Airbus. As an engineer, the clients will tell the company that I want an aeroplane with 500 seaters or 600 seaters, okay? And that should fly directly from Delhi to, let's say, Newark, long distance. And it should fly probably not in 12 hours or 8 hours, it should fly in 6 hours. A client can tell whatever he wants, right? Okay. The company will give the job to the engineers. Some of you will be those engineers, and tell that, man, I got so much money from a client. I don't want to lose this opportunity. You have to bring me a structure that will withhold this speed, because if I have to go from New Delhi to this place in this many hours, this is the speed that I need. You don't have to, I'm not talking about the engines that you need. Okay, let's say the engine can be designed. That's the difficult part to design, most difficult part. But let's say that is design. He will tell this is the speed, right? My wings have to be strong enough to take this speed. Okay. It has to be light so that I can fly so many people. So my weight of the structure has to come down. Okay. But it cannot bend too much. So it cannot be like a wing of a bird that it bends so much. It has to be robust, strong. And then it's your job to find the material to do that. Okay. You may not have any material in the world. You have to tell your company boss that there is no material available in the world that will do this. Then he will say that, okay, if one material cannot do, combine materials. So you have to go for metal composites. You have to find a proper composite that can withhold that load without giving you a lot of deformations, and also light. So your constraints are coming into picture one by one. So that's where center material comes into picture. That's the beginning where you start understanding what are the factors that need to be discussed for design and how you're going to design, right? Okay, enough talking. So we in strength of material, we look at 3S. One is called strength, one is called stiffness, the other one is stability, right? These three are called 3 pillars of strength of material, right? So strength is, as I discussed, is the load carrying capacity of the material, and it's given in terms of stresses, right? So we talk about not about force in strength of material so much. We talk about sigma, or stress of the material or the structure, which we call strength. Stiffness is mostly related to deformation or strain, related to deformation or strain, epsilon. Okay, these are standard notations for these variables. And then stability, okay, which combine both of them. So these are the 3 things we need to look at. One is strength, that means how much load carrying capacity it has. One is stiffness, that means how much deformation it can go. For example, I will give you one very very simple example. Suppose you are going to buy a house, okay, and you go inside the house and you see all the beams probably, or let's say floor, okay, all the floors are sagging, that means they're bent. So you have this, let's say, house, and you see the floor is bent like this. Even an engineer, tells you, oh sir, it's okay, you don't have to worry, it will survive. Will you buy that house? Probably not, because it's a psychological factor. Let's say there is a bridge that connects 2 points of a river, and it's a rope bridge or something, right? So as and when you stand on the bridge, it starts swinging. Although from years, a lot of people have crossed the bridge. Okay. For you, if you want to do it first time, you will have a lot of psychological fear factor there. Oh my God, I may fall. Because it's when, as soon as you put your foot on the bridge, it starts swinging, right? It starts moving. These are called psychological factors. These are called deformations or displacements in the structure, right? And it creates a different kind of feeling in human beings, even if the structure is safe or not. And therefore, there is a restriction on deformations also. Apart from larger deformation, it can break. There are issues with that, but even then, there is a psychological factor, even if it doesn't break, right? So that also has to be part of the limitation. Okay. And then stability. Stability is another factor that is very important. If your structure is not stable, nobody is going to get into that structure. Okay. That's very, very true. For example, you have a ladder and you want to go on to the second floor of the roof, and you get onto a ladder. And as soon as you put your foot on the ladder start moving this side. Will you go up? No, you will first check whether it's falling down or not. If it falls down, you will not go up. So stability is also very important. Okay. So these three things is what we are going to learn in this course: strength, stiffness, and stability. We'll first learn strength, then we'll slowly go to stiffness. Then one chapter will be there with stability of the structure. So these are the three things. At the end of the course, you should tell that, yes, sir, I know what is strength. You give me a material, I'll tell you what should be strength and whether it can carry that load or not. You give me a structure and tell me its material, I'll tell you what, and the load, I'll tell you what deformation it will get. So I know what is stiffness. And also I can talk about stability of the structure. Okay, that's I want all of you to tell at the end of the course, yes, sir, I'm confident in all these three parts. Right. All the stiffness, stability, and strength depends on definitely on material properties. Okay, that's the first thing. If material property changes, everything of this will change. They also depend on geometry and boundary conditions. When I say geometry, I mean the cross-sectional geometry, whether it's a square or a circular or a triangular or a complicated geometry cross-section. That's what I'm talking about, whether it's a straight rod or the tapered rod, all this is important. When I say boundary conditions, I'm talking about whether it's fixed, or a simple support, whatever, the boundary conditions is important. So these three things, whenever we talk about a structure, these are the three things you should first come to your mind. What material it has talked about? Okay, it's aluminum, it's steel, it's wood. Okay, fine. Or it's a composite. Then you should look into geometry. Okay, it's a cross section is how it's a square cross section, it's a rectangular cross section, it's a straight beam, or it's a tapered beam. Okay, if it's a rod, what kind of rod? Circular rod? No, it's a square rod. Okay, then this is what I have to do. What are the boundary conditions? Okay, these are the boundary conditions. These are the few things that should come immediately to your mind given a design problem. Right. This is what, when we talk about strength of materials, a material has following processes, in mechanics. What we deal with is the mechanical properties and theory. This is what we deal with. So many of the mechanical properties we learn in our strength of material experimental labs, and theory is what you learn here, a part of it, not fully, but it's the starting of discussion. A few more discussions are here. We will mostly solve our problems for bars. Remember, these are examples will be shaft, which will take torsion, then beams, and finally columns for stability. These are our applications of what we theoretically learn. Okay, so the full course, the development will be understanding the logical development of concepts like strength. Okay, strength, we'll learn about what is strength in this course. We'll learn about what is stiffness, and then we'll learn about stability through stress, strain, deformation, and material properties. An application of those concepts to rods, shafts, beams, and columns. This is what the course is. Okay, flow in mechanics. So we talked about what are we going to deal with in mechanics. We are going to deal with 3 A's: strength, stiffness, and stability. And all these three depends on material properties. It depends on what are these material properties. We'll discuss in few classes after. It depends on geometry, boundary conditions, right? So how does these things come up? How do you relate them? We all see that when we have a structure, we see the load coming to a structure, right? And finally, we say there is some deformation. Suppose you take a scale. If you have a scale in front of you, a ruler, you hold one side of the ruler and put a point load in the other side. Put a finger with some load. You will see the material scale will deform slightly, right? So you can see that you're giving some load, some force, and you will see that there is some deformation. So these are the two visual things that you can see. One is the point of application of the load, right? You may not see what is the amplitude or magnitude of the load unless you put a sensor there, and visually you can see a deformation. Also, again, you cannot measure unless you put a measurement device there to measure the deformation. But these two is roughly visible things. But what happens in between, right? So if I have to see roughly what happens in between, I have to see like this. So external load that is there that you can see in the structure becomes internal forces that you have understood, BMD, SFD, and internal forces. Those internal forces give rise to something called stress. So stress does not depend on external load, it depends on the internal load, okay? And that stress gives rise to something called strain in the material. We'll tell what are these, okay? And the strain gives rise to something called deformation. And this is also what you can see. Therefore, there are two ticks here. These are what you can see. You can also measure strain from deformation, back calculation, using some strain gauges, okay, that are used to measure strain. So that gives strain as an output, but still it is based on deformation. Now, when you go from external load to internal load, you use something called free body diagram and equilibrium of forces. Okay, equilibrium equation. Right? But when you go from internal forces to stresses, you use something called differential equations of equilibrium. Differential equations of equilibrium, not the same equation, or governing equations of equilibrium. Okay, we will develop this. Don't worry about it. So from internal force, you go to stresses, and from stress to strain, how you go? You use something called material models or constitutive relationships. So these are called material models or constitutive relations. We learn from 1D and 2D structures in this course itself. In a month's time, what are these and how to develop these equations? We'll learn it. From strain to deformation, use something called strain deformation relationship, which we'll learn probably in 1 week or 2 weeks time. Okay, strain deformation relationship, which gives you strain to deformation. So this is called a forward problem. This is a forward problem from force to deformation. Similarly, you have something called an inverse problem, which is from deformation to the force. Okay, here we move from deformation to strain, strain to stress, stress to internal force to external force. This is the inverse problem. So you calculate deformation on the body, and from that deformation, you try to understand what kind of external forces is acting on the body. Okay, so this is a little bit of complicated because of a lot of steps in between, and these are not one-to-one relationship, and therefore there can be a lot of external loads that can give rise to same deformation. So the forward problem is easy, but the inverse problem is not easy. Okay, except for a few simple problems. Enough of talking. We just discussed few things. I will try to stop here because I'll not define stress today again. I will talk about stresses in the next class because let it be fresh in your mind. If you are stressed, let us this photo has been taken from internet. Let us stop here.